We do. We see. We hear.
So it's a pleasure. So thanks for this this warm introduction. I'm happy to be here and to share with you part of my research interests. And for this, I would say my disclaimer for today would be that I will focus on outcomes that will deal with optical imaging at the end of the talk to be in the framework of this session, but still keeping the spin-orbit interaction of light as the key physical process at work in all the manifestation I will present. These manifestations deals with light-matter interaction at large, and with a specific feature which consists of the topological defects, as suggested by the title. So I move on, and I decided to actually to have two aspects for these talks: soft one and I would say more solid state one, as you will see, to go from natural approach towards technological approaches, and to see how we can get benefits from both. Of course, from technology is quite obvious for us as a researcher and developing future technologies, that technologies is solving some problems. One of our an asset in a group is to develop, I would say, nature-assisted technologies. So for that, I will need to present what I mean by that and which kind of elements we will use. And instead of making a review, I simply choose a couple of illustrative examples through which I would manage to convince you about the why this can be useful and what is the key ingredients from physical point of view. So let's start with what I call soft optical materials. So it comes from the vocabulary, soft being the capability to be rearranged in space. And for that, we'll make a switch back to the late 19th century, when a carrot entered the history of science, when researcher Reitnitzer discovered what we call now the liquid crystals. Actually, liquid crystals were extracted from carrots. And all these stories of these beautiful photonic materials is starting so more than 1 century ago. And here in the bottom, you see a picture of Lehmann, a physicist, to which Reitnitzer sent his discovery, this material, because he had the intimate conviction that this material deserves the interest of physicists in terms of their physical capability, structure, understanding, and so on. So this was really the beginning of liquid crystal science at that time. And I do like this picture on the right, where you see it's a handwritten photography by Lehmann, looking in its crystallization microscope that we can see here on the left. And you can see some structures. You can see some black and white. Black and white means two phases, an isotropic phase, and at the same time, the liquid crystal phase as such, where light passes through is cross polarizers, and then there is some brightness represented here in black and white by simply white, and some structures, as you can see here, kind of crosses spread in a random manner in the field of view. And so these kind of elements of materials, there are a wealth of phases, and the most common is called the nematic liquid crystal phase. In this phase, the molecules, you can consider them as a physicist as anisotropic molecules. So let's say cylinder for a simple drawing. And the orientation of the molecules are locally parallel one to another. So somehow that's the orientational order of liquid crystal, and that's the way it is expressing its ordered feature, still being a fluid. It can flow as oil. So these materials, if you left them, I would say without any external constraints, so this is what I call the left in the wild, they express in a very distorted way. This picture is a cross-polarizer optical microscope image taken between so cross-linear polarizers, and you can see structures. You can see black and white, you can see the same crosses we saw the last slide. And these crosses actually refer, if you analyze them properly, refer to a topological structuring of the orientation defined by this unit vector called the director. So there is a well-defined spatial orientation around specific points. Those points correspond to the core of topological defects, around which there is a well-defined structure that you can label with a topological charge, with alpha integer in the present case for this nematic liquid crystal. So this is just one example how liquid crystal can express a variety of a spatial structure. But if you want to get benefits from, I would say, a well-targeted benefit from a liquid crystal, from this anisotropic and soft material that you can reorient, typically with electric field, so nothing new. This is all liquid crystal displays we are used to have everyday life. And for that, we have to tame liquid crystal in order to tame light. So we are organizing the liquid crystal in a directed manner. That's the technology in order to structure light in a directed manner, for instance, to get imaging. And in the present case of a display, we're dealing with structuring the optical intensity and its variety of color, of course. However, not only liquid crystal needs to be tamed, and that's my point. The electromagnetic fields are also wild guys in the sense that any of their property that I summarized here by amplitude, phase, and polarization state could express random structures and or topological structures. So I give 3 examples. For amplitude, this deals with caustics that you can simply observe looking in the bottom of a glass, for instance, or the bottom of a swimming pool, owing to the motion of the water surface. That radiates light into streams of bright spots. Looking at the sky, looking at nature, you can also observe some structural features, topological features related this time to polarization. And this is very old physics dating from Brewster in the 19th centuries. So, and phase as well. Phase, this is embarked in the simple physics of random field, a speckle field. Take a laser, take a rock surface, observe this granular specular reflection, and then you get this this structure. And this structure actually is the one I will continue to talk on, because this structure is actually associated with the phase structuring, with the phase topological events that I present here in a very simple experiment. I just take a laser pointer, sandpaper. I'm looking. This is just a picture of a screen on which I just added a reference laser beam, quasi-planar waves. And if you look closely, you see fringes, and those fringes are broken in the sense that some forks could be seen at some places, up or down, depending on the place you look at. So if you want to understand this, since intensity distribution relates to phase in interferometry, this means that we have kind of broken phase because we have a kind of broken intensity pattern. And to get a more generic view about this, let's simply simulate a random field, taking a numerous number of random plane waves and look at the phase of them. And the phase here, as you can see, you can appreciate the existence of particular points where all colors meet. All colors means that all values of the phase are expressing at the same time at a given place. Of course, this corresponds to null intensity, because all phase at the same time means the phase is undefined, and this is a singularity for the phase field. And this is what we call, in a generic manner, optical vortices. And if you look closely, the color winding, it could be either from red to blue or from blue to red, choosing a clockwise or counterclockwise direction, for instance. And this leads to the emergence of only 2 topological charge, plus or minus 1, which means 2 pi or minus 2 pi as you make the run of the clock. And that's all what you can get from nature. this plus and minus 1 optical phase singularities. But since we are dealing here with mathematics, we can simply write even more charged singularities. That could be any integer. And here, to construct this is not a problem, of course, this is just computing. But to master them in the lab towards technological development implies to force nature, to force light to adopt this configuration, which are not stable biases, as discussed in the previous slide. So, and this is the topological optics of paraxial fields. That can be expressed in a variety of bases, and maybe the most famous one is the Lagrange one, where you can see here there is a phase factor for each of the elements of the basis that is associated with one of the phase singularities here, and there is an infinite number of them. They are used in a variety of application fields. A few of them have been already already discussed by the previous speaker. And here I will show all different kind of options to get them and to use them purposely. So keeping liquid crystal as the nice optical materials to do that, just have to realize that, of course, there have been technological developments since the emergence of the liquid crystal displays from the 60s already. And this spatial light modulator made of typical megapixel matrix of liquid crystal elements that can be controlled individually in an electrical way. And the idea is that those devices allows the light that passes through or reflected off a given pixel to change the phase that depends on the applied voltage. So the phase, the propagating phase, which we call the dynamic phase, is modulated by electrical means. By doing so, you can create on-demand arbitrary phase masks, still pixelated. This is very convenient, and most of you and many people around the world got this nice device in their lab, doing optical physics with this. And my point here is, as I was explaining at the very beginning, that we'll not go towards exploration of what we can do with liquid crystal spatial light modulators from the technology, but how we can access to similar features or even better ones by simply taking nature as it is expressing itself. So the concept that we pushed in the group since several years is the following: is simply to recognize that these two pictures share similarities. On the left, liquid crystal picture you already seen before. On the right, a phase profile of a random field that you already seen before. And the point is that the analogy is very tempting to say, oh, I can make some connection between the orientation, between the inhomogeneity of an anisotropic material and its topological charge with respect to the electric field of light and the topological features it can be endowed with. And this connection is made by a physical ingredient, and this physical ingredient is a generic one, which is called geometric phase. The geometric phase and embarking geometric phase in optics means that we are dealing with reference frame. And think about this, if you don't know this physics, think about this as a time zone effect for the phase of the light. So you're in Paris, there is a given time, you go to Japan, you need to change your clock. If you go to States, you need to change your clock in the other way around. And this means that depending on the way you are rotating, being light, you will experience different phase delay in opposite direction, depending the reference frame is rotating from right or from the left. And this effect actually is at the root of manipulating the phase from a homogeneous and anisotropic media. Or it works more quantitatively. The idea is simply to choose and to play with this circular basis. And to take a very simple case here, and the idea is not to go into details of what we can do with that, but just to catch the key element. The key element is the half wave plate. So you imagine a uniaxial medium, an isotropic medium here, with an optical axis along this arrow, and that imparts simply a pi phase shift for incident light. So circular right becomes circular left, but there is a phase delay which is associated with this local frame positioning in the lab frame XY. And from this boundary, more than 19 years ago already now, understood that we can build simply by shaping spatially the orientation of the optical axis of anisotropic material. We can shape the phase of the outgoing light emerging from such a system. And after 25 years of developments, liquid crystal community, optical community developed many interesting tools that can manage with higher spatial resolution, monochromatic lights, or with less nice resolution in a wavelength tunable manner. And this kind of device are commercially available as well. So that's the beginning of a new technological era, I would say, that goes beyond the liquid crystal spatial light modulator. However, you don't have the best of the two worlds. It's not high res and tunable. And this is my question: could we use nature to combine all these assets in a single device, and at the same time getting rid of technological developments, if we could? So for that, let's be back to just another picture of liquid crystal thin films. We are speaking here typically a few tenths of micron thick liquid crystal. Here we have a field of view of, let's say, millimeter square. And what we see in this configuration, another kind of defect structures, 4 branches, 2 branches at some places. And if you unravel this with proper characterization tools, you can unravel different kind of defects, this time, again, from -1 to +1 by half integer steps. And if you use any of them as a geometric phase optical element, tuning the phase, the local phase, as working as in a half wave plate condition, imparting a pi phase shift for orthogonally oriented electric field components, then you get this topological transfer between the information of the matter to the information of light. Here, the incident light is a simple Gaussian beam reading out the topology of the liquid crystal topological defects, experiencing the spin-orbit interaction, embarking geometric phase optics physics, and the output field is it's a donut beams, it's a vortex beam, and you can check that by interferometry that you have a phase singularity, you have spiraling arms with different underness, positive or negative charge, and with different number of branches associated to the charge. So, but this is not all, because it's a liquid crystal. The phase can be tuned, and you can adjust it to the wavelengths you want to play with. So simply by changing the voltage by the couple of tenths of millivolts, you can simply adapt. Here is just an example for covering all the visible. This is a given element. You simply need to tune the voltage, and then you have a fully tunable experience of the vortex generation. Still, this remains random events. So this was typically this kind of things here. Random events, nice operation, but random events. So if you want to turn this into a really user-friendly devices, you need to get control about this self-engineering. So the idea that we developed a few strategies to direct the self-engineering. So the idea is not to tame in a hard manner the system, but simply to tell the system, go there or go there from a topological point of view. And an example is shown here at the macro scale, building up a macroscopic device, 1 centimeter aperture, really like a usual device, simply using the same nematic films that alone gives a random mess of nice structures. If you simply place a ring magnet, you will transfer the topological information embedded in the magnetic field lines that will be experienced by the nematic liquid crystal. and that will emerge as a nice single topological defects once the electric field is applied. So this magnetoelectric approach is working very well and provides in 1 minute an element, I would say with high capabilities in terms of resolution. It's kind of perfect one provided by nature, and it's fully tunable. So beating any device of the day, I would say, in a very simple manner. Another example, at this time at the micro scale, that we are developing spatial light modulators made of liquid crystal, but this time not using usual liquid crystal pixels where the orientation is fixed and imparting a well-defined phase to light interacting with the pixel, but using structured pixels. Every pixel now is a topological defect spontaneously organized. The physics of liquid crystal is spontaneously engineering this. I don't need to engineer locally every pixel, and then you have a kind of SLM of SLM. So it's a kind of a really new approach to shape light in a very rich manner, and it's just the starting of exploration of what we could do with that. And I will illustrate in the end of this presentation an example of use in an imaging context for both the macroscopic approach and this microscopic pixelated approach. And just to highlight the flexibility benefits of using a soft self-engineered approach. So the first example is imaging the sky at night. You want to look at, for instance, you want to look the sun. You want to look the corona of the sun, and for that you are simply blind by the sun itself. And for that you need to block the main sunlight to enjoy the corona. And for that you need to wait for a total eclipse. So it's cool events, but it's rare events. So almost 1 century ago, an astronomer, French astronomer Bernard Liot, invented a way to do this on demand. And this was the early days of what we call now coronography. The idea is simply that to place a moon, an obstacle in the Fourier plane of a telescope, and to provide on demand an eclipse. Very simple. It's an obstruction of the zero spatial frequency in a telescope. So it's a kind of Fourier filtering technique applied to astronomical imaging. If you turn this in a vortex manner, exploiting the phase obstruction instead of an amplitude obstruction, then you get a redistribution of light, no longer blocking photons, but a redistribution of the flux of light. And there is a specific plane where there is a nodal area, an area of darkness, that you can simply fully extinguish by simply placing an iris, which is slightly smaller than this diameter. In that case, you can simply extinguish the light from the star and then recover the light of the off-axis, let's say, less bright elements that you won't see much in the presence of the sun. And that is simply going out from the background once the sun is extinguished. So nowadays, we have this kind of elements, macroscopic elements, in the embarked in all major telescopes to observe exoplanets. That's the typical use of this kind of elements. And this is how we use the liquid crystal for that, to do this in a very simple manner, no high tech. You simply take a liquid crystal defects and the coronagraph is off. The defect is not electrically activated. We activated it, and this simply airy spot is simply extinguished. This is log scale, so this is deep extinction by simply placing the defects at the right place in the Fourier plane. And there is no engineering. No engineering and capability to direct the topology morphogenesis, which means why not to extinguish multiple suns and to do something we cannot do today with astronomers to extinguish multiple star systems. But for that, we simply need to develop multi-topological tasking. And this, we can do this. We develop techniques to do that, to direct topological defects emergence at specific place and to extinguish on demand any number of sources and to have observation of dim sources nearby bright environment. So this is just an example. And regarding the microscopic world and pixelated self-engineering devices, here is an example of this spatial light modulator where every pixel is a topological pixel. This is the response of one pixel, so a nice vortex is generated. And what is interesting here is that we made a demonstration that dispersing a polychromatic field into several channels. Then you place your device here, this device, and you simply process every wavelength channel by a vortex generator that you can control on demand, one by one, in an independent manner. And you can tune every one of them in order to process fully every wavelength. And then you get in a far field, broadband, polychromatic, white light, which is very hard to obtain with other kind of techniques. And the previous speaker was mentioning dispersion, drawbacks. This is actually really something we have to manage with when we deal with polychromatic fields, as is the case usually when we do imaging on microscopes. And then here's an example. So I won't introduce the STED microscopy since we're in an imaging session. So I will assume that you're aware about these techniques. And the idea that if with this system we process all wavelengths, set of discrete wavelengths to be fully processed, this means the polarity is maximum, the vortex is maximal, and this is a half wave plate condition. It's an odd number of pi as a phase delay, simply tuning the voltage. So you get this white light vortex. And then the idea is that you take one of the pixels and you placed it in a way that for this color, you won't have a vortex generation. And then you have a central hotspot that will be the reading spot of your STED imaging system. And this spot, you can change its color simply by changing the voltage in a fraction of seconds. So you could read in a multispectral manner with the STED capabilities. So this is kind of things that we are developing. So since time is running, so there is a nice, there is a, sorry, not nice, but there is a few more slides, so I could skip them. Anna, you can just, there are 3 slides. I'm ready to skip them and to end here.
What do you think?
Maybe we can afford a couple more minutes. We are just, we should finish in maybe 5 minutes, so maybe 2 more minutes.
Okay, so 2 more minutes to explain what I call the modal challenge. Because so far I was just illustrating few very in a rapid manner and a very limited number of examples of phase singularities, also all the azimuthal shaping of the phase can be used for photonic purposes. However, if we recall the way a field can be described, it can be described with azimuthal phase contribution, but there is also another second degrees of freedom. The second degrees of freedom is the radial degrees of freedom. If you are Cartesian, you have X and Y to describe paraxial field. If you are in a cylindrical coordinate, you have azimuth and radial coordinate. Azimuth associated with the first part of the talk, but we are still missing all this radial information. And this radial information is really seen here in the development of Laguerre-Gauss modes as another index independent from the first one, L being the charge of the optical vortices of this basis, P being the what we call the radial order, the radial index of a mode, the number of oscillations in the along the radial coordinates for the wave field. And you can appreciate how a nice spiral phase mask, for instance, is doing the phase, the helical phase distribution. We know this well now. However, this is not shaping in a radial manner a given mode. And this, you can see it here. Any mode here is propagation invariant in terms of shape. And here you can see that the propagation after a plate, this is an experimental image, after such a helical phase mask, you have a radially oscillating intensity profile that depends on the propagation distance. So clearly, there is a superposition of mode. Actually, there is an infinite superposition of radial mode in this optical vortex field. So yes, there is a well-defined topological charge, the L index, but there is a huge number of P index. And if you want a mode, for instance, for optical communication, optical information, manipulation, or use, particular use, you need a given mode. So for that, you need to shape as well the radial degrees of freedom. How to do that? speaking with geometric phase, we are trapped with phase shaping. But if we recall that this process is, I was presenting it only in the half-wave plate condition, where delta parameter here is pi, and this term is 0. If you use it in its most general way, you can shape the amplitude by simply shaping the level of anisotropy of such a geometric phase optical elements. And by doing so, if you are only interested by a given circular polarization state, the one that experiences the geometric phase, then you can also modulate the amplitude. And then you have a spin orbit capabilities assessing complex amplitude modulation. We developed a recipe. I will skip that slide. It's just to tell that there is a theoretical background in order to shape properly the structure of an inhomogeneous anisotropic optical element in order to have at the output a given mode, for instance. Laguerre-Gauss beam will be L, P, and a given waist. We developed the first optical elements in order that could do such a modal spin orbit shaping, as shown here. These are nano-structured optical elements, macroscopic ones, almost 1 centimeter diameter of structuring. This is the azimuthal distribution of the optical axis of this half-wave plate. This is a standard element, which are really like a not model, and this is a given model element. Of course, there are still today some limitations. This is very recent work. And this limitation here is due to a subtlety, which is very nice. Physics is the one associated with the prefactor here. If you want to modulate in a radial coordinate the amplitude, you need to modulate the anisotropy level. If you modulate the strength of the anisotropy, at the same time you pay a price. You pay the price at the mean refractive index. As you want to change the anisotropy, you are changing the mean of the refractive index. And this, the price to pay, is dynamic phase modulation. And this spoils your efforts to have modal beam shaping. So the idea is to compensate this drawback with a geometric phase correction. And if we do that, we get rid of this term and we are back with a fully controlled mode shaping. Again, we developed the recipe, analytical recipes. I skipped them and just to get the spirit. And this is my last slide. Just to show that this is just preparation, just to share recent results done with colleagues in China, that we developed metasurface, dielectric metasurfaces in a visible range, enabling to transform a Gaussian beam with into a LP mode, exploiting the dynamic phase correction via geometric phase mean. So it's quite a, I would say, technical manipulation of light. However, it's working nicely, and we wish and we are working towards the development of this kind of technological approach. So I will stop here. I thank you for your attention, and I hope for those who were not aware about this spin orbit interaction of light, that you at least you have been a bit excited by what we could do for optical imaging. Thank you very much.
Thank you.